Section 4.2, Areas and Sums. Sigma notation. The sum of n terms, A1, A2, A3, all the way up to AN, is written as the summation as I goes from 1 to n of A sub I, which is equal to A sub 1 plus A sub 2 plus A sub 3 plus ... plus A sub n, where I is the index of summation, A sub I is the ith term of the sum, and the upper and lower bounds of summation are n and 1, respectively. Now, any variable can be used as an index of summation, but I, j, and k are used most often. The lower bound doesn't have to be 1, but it cannot be negative because it represents where we are in our number of terms in a series, if we're on the first term or we're on the fifth term, etc. Now, this page of notes is not tested as far as AP goes, but it's good to know. And you do not need to memorize these formulas at all. Here it says the sum as I goes from 1 to n of a constant is the constant times the number of terms. Number 2, the sum as I goes from 1 to n of I is n times n plus 1 over 2. The sum as I goes from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And the sum as I goes from 1 to n of I cubed is n squared times n plus 1, the quantity squared, over 4. Again, you don't need to memorize these, but let's see how we can use them. If I want to take I from 1 to 6 of I, that would be substituting in 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21. Here's a really neat way to do this. 3 plus 4 is 7, 2 plus 5 is 7, 1 plus 6 is 7. Notice that I have n was 6, n plus 1 would be 6 plus 1 over 2, which is 6 over 2 gives you 3 times 7, 21. Just kind of a neat little thing. I have a story involving Gauss on this, so remind me in class to tell you about it. Here's another problem. As I goes from 1 to 15 of 2i minus 3. Well, we can make two summations out of that. And what we have here is 2 times I, so I can take this, I can bring the 2 out in front and then use this formula. And this is a constant, which means this. So that means 3 15 times, 3 plus 3 plus 3 plus 3, until I've added it 15 times. Or I can do 15 times 3. So I have 2 times my sum as I goes from 1 to 15 of I, and minus as my sum as I goes from 1 to 15 of 3. Well, we know this using this formula gives us 15 times 16. We know this using this formula is going to give me 3 times 15, which is 45, and there's our answer. There's our sum. Okay, let's find the limit of the sum S sub n as n goes to infinity. Well, this should be easy. As n goes to infinity, we're talking about the limit as n goes to infinity of our sum. Well, what do I know about this? This is a constant. The limit as n goes to infinity on the constant is the constant. As n goes to infinity here, that's going to give me 4 over really big, which is 0. As n goes to infinity here, that's going to give me 4 over really bigger, that's 0. And so our answer is 8/3. Now we'll do a little bit more complicated one. This is kind of interesting. So I have the sum of 64 over n cubed times n plus 1 times 2n plus 1 over 6. Now, if you look at this, you will notice that this is essentially a cubic polynomial with a coefficient of 2. So when I go to take the limit as n goes to infinity, I have 64 over n cubed, and this is going to be 2n cubed plus a lot of other stuff over 6n cubed. Well, now let's think about this. We just learned about the limit as something goes to infinity, as n, in this case, n. The degree of the top and the bottom are the same, so it's going to be the ratio of the leading coefficient, which is going to be 64 times 2 over 6. Well, the 2 over 6 goes 3 times, so it's going to be 64 over 3. Pretty neat. I will leave this for you. You don't need to know how to do this, but I know you probably want to have it in your lecture manual, and we'll talk about it in class. We're really going to talk about area. Area under a curve is a really important concept in calculus. It can be approximated by dividing the region into rectangles, finding the areas of the rectangles, and adding those areas. The smaller the width of each rectangle, the more accurate the area approximation will be. Our trick is to find the width of each rectangle, and we're going to call that delta x. And that is going to be on the closed interval from a to b. So delta x is b minus a over n, where n is the number of subintervals. So this will make a uniform width. Then we're going to find the endpoint of each rectangle that we're going to use. That's called x sub I. Then we're going to find the height, which is found by substituting those x's into our function. And then we're going to find the area and add. So our example. Compare the rectangles formed at the left and right endpoints of f of x equals x squared plus 9 over the interval from 0 to 2 with 4 subintervals. And we're going to sketch this diagram. Note that it is not drawn to scale. What I want you to notice here, here's my function. I've drawn 2 sets of rectangles. I've drawn the set that are outlined in colored ink that are under the curve. And I've drawn the set that are in pencil outside the curve. This underneath the curve, notice that the corner is on the curve and the other corner is underneath it. So this area will be an under approximation. And notice that if I were to use the rectangles formed by the right endpoint here, where my rectangle goes outside the curve, that is going to give us a sum that is greater than the actual area. So underneath is called a lower sum, where every rectangle is underneath, and an upper sum is going to be where every rectangle goes outside of that area. You could look at these rectangles here. We call these rectangles a left-hand sum because the height of each rectangle is found at the left endpoint of each subinterval. Here's my subinterval, left endpoint, there's the height. Here's my subinterval, left endpoint, there's the height. So each of these colored rectangles lie below the curve. This is a left-hand sum. Now, not always will the rectangles, if they're from the left, lie below the curve. Here's a pair of left-handed rectangles, a left-hand sum, and those rectangles go outside the curve. Here's another pair of left-hand rectangles. The left endpoint of each subinterval lies on the curve, and the rectangle goes outside the curve. Notice both of these left-hand sums over approximate the area because the rectangles go outside of the curve, and this one, as well as this one, these are left-hand sums, and these under approximate because look where the endpoint goes on the function, below the curve, on the curve, and the rectangle's below the curve. Left endpoint on the curve, but the rectangle's below the curve. So for this function, since it is increasing, the rectangles formed at the left endpoint, so left-hand sum, will form a lower sum. Notice it is because the function is increasing. Notice that this function is increasing, and my left endpoint rectangles, my left-hand sum, form a lower sum. Rectangles formed at the right endpoint, right-hand sum, form an upper sum. So for this function, since it's increasing, the right-hand rectangles, the right-hand sum, will over-approximate. Again, I can come and look at this one. The right-hand rectangles will over-approximate. That is because my function is increasing. Now let us remember, it's very important. Your left-hand sum is not always a lower sum. It is in this case because my function was increasing. Your right-hand sum is not always an upper sum. It is in this case because my function is increasing. So how do I figure out how wide each subinterval is? Well, delta x is b minus a over n. My right endpoint is 2. My left endpoint of my interval is 0. And it says here to make 4 subintervals, so 4. So that makes delta x 1/2. What does that mean? That means the width of each rectangle is 1/2. Now, that means that my intervals are going to be 0 to 1/2 for my first subinterval, 1/2 to 1, 1 to 3/2, and 3/2 to 2. And making a left-hand sum would be to use the left-hand endpoint of each subinterval, evaluate the height by taking f of that left endpoint. So I'm going to take f of 0 times my width, which is 1/2, plus f of 1/2 times my width, which is 1/2, plus f of 1 times my width, which is 1/2, plus f of 3/2 times my width, which is 1/2. This is important in AP, showing your setup. And what did we just find? The sum from 1 to 4, 4 rectangles, my y value times the width of each rectangle. The y value is your height. The delta x is the width. So you could go over here to the side and find f of 1/2, f of 1, f of 3/2. Obviously, f of 0 is going to be 0 plus 9, which is 9. And we get these values. So that's 9 times 1/2 plus, we found this to be 9 plus 1/4 is 37/4 times 1/2 plus f of 1 is 10 times 1/2 plus f of 3/2 is 45/4 times 1/2. Now you will notice each of these has a factor of 1/2. So if you wanted to, you could factor out the 1/2 and add all these up, or you could do the math. But eventually we're going to get 19.75 for our left-hand sum. Now let's find the right-hand sum. How would you find the right-hand sum? I would use the right endpoint of each subinterval. And I would evaluate my function at the right endpoint of each subinterval. Let's remember, we were finding a lower sum designated with a little s. And because our function is increasing, the left-hand sum gave us our lower sum in this problem. So we got 19.75. Then if we want to find an upper sum, we're going to use the right endpoint, as I just said, denoted with a capital S. And we're going to evaluate at the right endpoints our function. The width of each is still 1/2. And we get, for this, we get actually, adding all those values up, 21.75. Now, notice that my left-hand sum, which in this problem is a lower sum, is 19.75 approximately. My upper sum, which happens to be the right-hand sum because my function is increasing, is 21.75. And of course, you can tell by looking at the diagram that my sum has to be, my actual area has to be between that, because these colored rectangles leave something out that's not counted, and the pencil rectangles count more than should be. Kind of like Goldilocks and that the 3 bears. Too much, not enough, and just right. Our actual area is just right. We don't know what it is yet. We could get closer to the actual area. What if we found the midpoint of each subinterval? If we use that, my delta x is still 1/2, But now my coordinate for the height is no longer an endpoint, but it is going to be the midpoint of each of these subintervals. So the midpoint is a fourth, 3/4, 5/4, 7/4. And again, my area is approximated by f of these. 1/4 times a half, f of 3/4 times a half, f of 5/4 times a half, f of 7/4 times a half. So this time I decided to go ahead and factor out that common factor of 1/2 and find here is f of 1/4, f of 3/4, f of 5/4, f of 7/4, add all that up, and then times a half gives us this. And notice my diagram is going to look a little different. Notice that in each rectangle, I have a little bit being left out and a little bit being added that shouldn't be added. So that might give us closer to our actual area. And it is between our lower and upper sum. Now, note that this is not the average of my upper and lower sum. The average of my upper and lower sum, and in this case, the left-hand and right-hand sum, is 20.75, which is not this. So we're going to talk about this in upcoming events. Now, does it make sense that the area found by the midpoints is between the upper and lower sums? It does for this problem. Again, be careful. Midpoint sum is not always the average of the upper and lower sums. Now, we will be doing several of the following pages in class. So here is your 1 TP for this section. See you next time.